Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to discuss entropy changes for an ideal gas. Now the equations that we've developed so far, as we said earlier, they apply to any and every situation: solid, liquid, gas, real gas, ideal gas. So for all practical purposes, we don't really need to take those equations and somehow fiddle around with them in order to apply them to the case of an ideal gas, because they apply as is. However, it's nice to do this because most of the time when we're dealing with gases, unless we're doing really specialized work, we're always going to treat a gas as an ideal gas. So it's nice to have some equations specifically for ideal gases that you can just sort of turn to when you know you're dealing with an ideal gas. You don't have to if you don't want to. Again, all the other equations are absolutely valid, and if you want to do the derivations for yourself, it's always nice mathematically and personally. It gives you a nice sense of accomplishment. But I think it would be nice to go ahead and actually discuss it specifically for an ideal gas, because it does tend to be the system that we talk about the most. So let's jump right on in. Okay, now what's nice about the equations for an ideal gas is that they tend to be really, really simple. So let's go ahead and start off first of all. So we're going to do a little bit of a mathematical derivation, very, very quick one though. So in general, you remember that we had, for energy with respect to temperature and volume, the differential change in energy was equal to CV, equal to CV dt plus du dv under constant T dv. But because we're dealing with an ideal gas, what's nice about it, you also remember, hopefully, for an ideal gas, this term, the du dvt, it was equal to 0. That was Joule's law. So for an ideal gas, this change in energy with respect to a change in volume under constant temperature actually equals 0. This was Joule's law. So when you change the volume of an ideal gas, you don't change the energy of the system. That's what that says. So basically what you have, when this term goes to 0, what you're left with is just that. So we have du is equal to CV dt. So now we'll go ahead and put that aside for a second. Now let's deal with the fundamental theorem of thermodynamics. So the fundamental theorem, of thermodynamics, it says the following. It said that ds is equal to 1 over t du plus p over t dv. Well, we have du under conditions of an ideal gas, so we'll just go ahead and put this into here. So what we end up with is ds equals 1 over t cv dt plus p over t dv. So I'll go ahead and write this as ds equals cv over t dt plus p over t dv. Now, this particular differential, it looks familiar. It doesn't really look altogether that different than what we just did with the other equations. It's the same equation. Notice this is a function of temperature and volume, but notice we have pressure here. Well, the ideal gas law, again, we're dealing with an ideal gas, so it makes things simpler. We have an ideal gas law. We have a relationship between pressure, volume, and temperature. So because this is temperature and volume, every single variable in here on this side has to be expressed in terms of temperature and volume. So this pressure, we have to express it in terms of temperature and volume. Well, we can do that. It's right here. The P equals nRT over V. That's it. I take this and I put it in there. So here's what I get. So ds is equal to CV over T plus nRT over V over T dV. The T cancels the T, and I'm left with the following equation. ds equals CV over T plus nR over V dV. This, when we consider entropy as a function of, I forgot my differential here, dt. When we consider entropy as a function of temperature and volume for an ideal gas, this is what the general equation takes the form as. It's CV over T dt, that part is the same, plus nR over V dV. In other words, the number of moles times the gas constant divided by the volume of the system. This is the differential coefficient for the volume component of the entropy. That's it. That's it. Let's go ahead and call this equation 1. So for an ideal gas, this is the equation that you want to memorize if you want to. It's pretty easily derived, so it's not a problem, but there it is.